All right, here we go, guys. So this unit obviously ties right into the last unit, which is the periodic table. You'll still need your periodic table. Use the same periodic table. We need to keep labeling that thing, keep making it look really good. You can use it on a test just like before. So this one, let me scare out there. You're on YouTube now, Emma, so good deal. No. So this one's about stability and bonding, and it's going to go right with it. So I'll give you a second to write in some of this stuff. And guys, always remember, you don't have to write everything that's up here on this slide. You could always go back in Google Classroom later and fill in things you need to fill in if you didn't have time to write the stuff in right now. But if you have time, write it. But be able to think. Be able to think and ask questions and not just write frantically, because these notes will be where you can access them. So it says there on the first line, most elements are not found by themselves in nature. And so a good way to think about that is to think about the air in this room. Okay? What did we say? Does anybody know the most common element in the air? That's what I would have guessed, oxygen, but that's not actually it. That's a good guess though. It's nitrogen. That's right, It's nitrogen. And actually about 78% of the air in the room, that's a lot of it. Like, it's crazy, like 3/4, a little over 3/4 of the air is nitrogen. But the funny thing about it is it's not just nitrogen. Okay? Nitrogen is not just N. We call it molecular nitrogen. It's N2. So it's a nitrogen atom bonded to another nitrogen atom. That's how it really exists in the real world. You'll never find nitrogen by itself, just hanging out a nitrogen atom. You'll find it as N2, nitrogen bonded to nitrogen. Same thing as oxygen. Oxygen's not just an oxygen atom in the air. It's oxygen bonded to another oxygen atom. And that's the way most everything is. So most elements are not found by themselves in nature. What element, if you were to think through on your periodic table, what elements do you think don't obey this? If you had to pick one, we said most elements are not found by themselves in nature. So we just gave some examples. Which elements are found by themselves in nature? What do you think that would be if you had to make an educated guess based on what you know about stability? What elements are the most stable on the periodic table? Metals? Yes. Did y'all hear what she said? Noble gases. What Aubrey said? Noble gases. So that noble gases, that's very good. Noble gases disobey this, sort of. They're found by themselves in nature. Okay, so we have a compound. So the definition of a compound, two or more elements chemically combined. And the properties of a compound are very different from the properties of the elements that make up the compound. So check out this, guys. This is really cool. Sodium and chlorine are very different than sodium chloride. So have you ever seen sodium metal? You know what it looks like? I wish I had some in here. You know what it looks like? Sodium metal, pure Na. It's like a shiny putty. You know what silly putty looks like, right? That's what this looks like. Sodium metal looks like a shiny putty. And you can squish it in your hand. If you were to hold it, it's soft enough where you could mash it, which is pretty crazy. Chlorine is a gas, it's Cl2, and this is really dangerous. Chlorine gas will kill you if you got exposed just to chlorine gas. So you have a shiny metal that you wouldn't like eat, right? And you definitely don't want to eat any chlorine gas. That would be really bad. Okay? But if you combine the two things in a tube, put a little heat in with it, shake it up maybe, you get a chemical reaction and you get table salt. We're going to find out. That's a good question. That's kind of the point here, is to figure out. Cully, that's what we want to do, is figure out how sodium and chlorine combine together to make sodium chloride. And we will. We will figure that out. It's pretty cool. It's pretty cool when you think about it like that. It's like, how can these two strange things that are weird come together to make something you literally eat every single day. It's like essential for you to eat every day. That's pretty cool. Okay, well, let's keep rolling. So, chemical formula. So, anybody want to read this? Got one no, two no's. Kyle, you want to? Yeah, thank you, sir. Appreciate it. Yes, sir. Okay, that's all it is. So, guys, tell me, you've done this, I think we've done this. How many hydrogens are right here? 2, exactly. That's all it's saying, right? The number tells you, it comes after it, right? So, water contains two atoms of hydrogen and 1 atom of oxygen. Right? Well, there's not a 1 right here. So if there's not anything there, it's understood to be a 1. You don't write it as H2O1, but you could think about it being like that. It's H2O1, really. Okay? Even though it says H2O, it's H2O1. Because there's 1 atom of oxygen. You can think about the symbol represents the 1. Then if there's more than that, you put the number. That's what it represents. So how many N's we have here? Yeah, 1. Yep. And we have 3 H's. So ammonia is NH3. And water is 2 hydrogens, 1 oxygen. And that's it. That's it. So that is kind of the thought process behind how you figure that stuff out. Here you go. Yes, a new one. Okay. So that's all it is. Just saying the chemical formula. So if you have a big molecule like glucose, glucose is C6H12O6. Then that's 6 carbons, 12 hydrogens, 6 oxygens. C6H12O6. And so these chemical formulas are going to be important. Obviously, when we do bonding, because how these we can predict how things are going to interact with each other depending on, because it's all about bonding, guys. All of life really is about bonding. Like when you for chemical reactions to be able to happen in your body, that's how you work, right? You don't live without chemical reactions take place. There's like probably billions or maybe trillions of chemical reactions happening in your body right now, just sitting here, literally making you be able to think, breathe, do anything. And you think about that, that's kind of crazy. Literally for your brain to be able to do anything, chemical reactions have to take place for you to be able to release those neurotransmitters, even for your muscles to work. That's insane. Like for you to be able to talk, blink, it's all chemical reactions going on, making things work. That's it. It's nuts. All right. I should have asked this first. Did y'all see the answer? So this is a question for you. Why do you think, so we said before, it's a big question. This is huge. Why would an element like oxygen, like nitrogen, why do you think elements form compounds? Why don't they just stay as regular elements? What is it about? Why would one nitrogen, why did the nitrogen just stay by itself in the air? Why would it bond with another nitrogen? This could be any answer. Does it attract? Why do you think it would be attracted to? Put this to what Aubrey said about noble gases. Noble gases are what? Non-reactive. So in other words, they're stable. Okay? So, and we said noble gases are kind of like the cool elements, sort of. I guess you'd know, well, maybe not the cool elements. Just like elements everybody wants to be like. They're the ones you want to aspire to be, sort of. You think about that? And so, if the noble gases are the elements that everybody wants to aspire to be, and they're the ones that are non-reactive and stable, then why do elements form bonds? To become stable. That's it. It's stability. That's what chemistry is about, guys. Chemistry tends towards the more stable state because it's the lowest energy state. That's what we're going to see. That's how bonds work. You can predict it a little bit. So, why do elements form compounds? This will be a test question asked in 5 different ways, right? So, why do elements form compounds? To be stable. To be stable. That's the That's the reason. An element forms a compound so that it becomes more stable. That's the reason. So nitrogen bonds with another nitrogen atom because that molecule is more stable than a nitrogen atom by itself, as what we'd call an ion, which we'll learn in a second. All elements want to be stable. You know, they don't want anything really. It's really just about, they don't have a mind. But, so we kind of talk about these things as though they're living or something. But elements want to be stable just, I guess, energetically. They want to, it's easier to exist at a lower energy state. So what do you think of when you hear the word octet? How many? 8. Yes, 8. So the octet rule probably has something to do with the number 8. And it does, right? How many electrons can fit in the second energy level? 8. How many electrons can fit in the third energy level? 8. That's the octet rule, guys. The octet rule is saying that most atoms, it should say most, but it's not all, but most atoms will gain, lose, or share electrons in order to have 8 electrons in their outer energy shell. Is there another word that you can think of, that you could replace outer with? It talks about the outer shell electrons. What else do we call those? Okay, the electron cloud in general, yeah, kind of. But what about just the outer shell? Valence. Nice, Lucas. We call it the valence shell. So you could replace this. Most atoms will gain or share electrons in order to have 8 electrons in their valence energy shell. You could say that as well. The bonding shell. You could say that as well. And so when we say an atom is most stable, full complete outer shell of energy level of valence electrons. And notice it gives you the exception down here, right? Because there are exceptions to the rule almost always in chemistry. It says 8 for every element except for hydrogen and helium. Okay? Because hydrogen and helium, they're little bitty. You know, helium only has 2 in its outer shell because that first energy shell can only hold 2. And the same thing with hydrogen. They're tiny atoms. All right, cool. If any question pops into your brain, if you want to restate anything that we're saying about this stuff, do it. Let's have a conversation, not just me talking. Just get some talking from you too. All right. Okay, guys, check out this picture. I'm not gonna put anything up there yet. Is this in your? Okay. So let's just look at this. Look at sodium. This is sodium metal, right? It's an alkali metal. How many electrons in its outer shell? 1 in its valence shell. So think about just for a second what the octet rule said. The octet rule said atoms are most stable when they have how many in their outer shell? How many? 8. What would be easier for sodium to do? Just think about it in terms of like what would be easier for you to do. You kind of think about, huh? What'd you say? Give it away. Give it away. Do you see that? So Cully just predicted what sodium will do in a chemical reaction. That's what it does. Is it will give away that electron. That electron, what we see, and which if you remember, it's not held tightly at all. Because remember, the reason that electron stays there at all is because of the positive pull of the nucleus from the protons. But if you remember too, this electron is shielded by all these other electrons kind of repelling it. And so sodium will give it away. It'll give it away. What do you think chlorine's going to do? It's going to get one. Is that not a match made in heaven? Is that not like love at first sight? You see that man, it's like, that's the one. This is it right here. This is the match made in heaven, sodium chloride. Okay? Now this relationship, we'll learn, is a little bit, maybe like some relationships, I don't know. It's maybe chlorine's kind of a bully, and if you think about it that way, because chlorine kind of just takes sodium's electron, just steals it straight up, and doesn't give it back. Doesn't even share it with it. But you're right. Sodium doesn't need mine, and it's happiest like that. So maybe it's good. Who knows? Maybe chemistry can teach us something about. So that's what happens. You just predicted it, guys. Really cool. Sodium gives his electron to chlorine. Chlorine now possesses it. Chlorine's happy. Sodium's happy. And now what we have is sodium chloride and what we call an ionic bond. Very good. Very good. Fantastic. Fantastic. So, guys, this is what happens here is, and you know, it's so cool that you figure these things out, that you predict it. It's not told to you. You figured it out. You figured it out. So here was what it says, guys. Notice this electron, really, it doesn't go over here. It gets pulled over there. You know, it gets made to come over there by chlorine. Now, sodium's outer shell is full. Chlorine's outer shell is full. And we have a stable compound. So this is how the bond happens to form sodium chloride, table salt. The famous table salt. Okay. Let me see how far we want to go here, guys. What's the rest of? Let's see how many more.
This is the last one.
This is the last one on that page. What's on the next page?
We don't.
You do have that page.
It's right here.
Oh, okay. Okay, let's do the question. Let's do the question, and then we're going to be done for today, okay? So, dang it. The thing's up there. All right, stay with me, guys. Here we go. So, and I put the answer up there. Would elements ever not benefit from forming bonds? And we actually answered this before, right? And tell me. Yes, it's yes, but we put it up there. But why is it yes? No. They're already stable. Yeah, they're already stable. Look at their... Good, Nathan. Is its outer shell full? Yeah, is its outer shell full? Yep. It's the noble gases, right? We already stated it. It's the noble gases. So they're already stable. So it's like we said, some elements are already... That's just answering that question at the bottom of the page. Would elements ever not benefit from forming bonds? Yes. If they're already stable. And this is what we said. This is why the noble gases are non-reactive. Like the song says, this is the periodic table, noble gas is stable. That's the why they say that. Oh shoot, thanks. Yes, I'll no rights, all rights to the periodic table song. Yeah, I don't want to. Okay. Maybe for educational purposes it won't matter. I don't know. But anyway, guys, that's the. So what we'll do is we're gonna. So their outermost energy level is already full. We'll start back with bonds on Monday. Okay. We'll get into the types of chemical bonds and go from there. Questions? Nope. All right. Good, guys.